Okay, hopefully this is the last one of these for chapter 15, and we're going to look at one more of these types of problems that we might sneak into. And now we're on page 366, and we're going to look at number 35, luggage. And this is a question that the textbook wants you to use the tree chart with, and I don't like the tree charts because I don't feel that they're as intuitive. What we're going to do is we're going to create a conditional distribution table, okay? A contingency table. And this is actually really easy to make. And it'll give us a ton of information and make this easy to do, okay? So 35 reads luggage. Leah is flying from Boston to Denver with a connection in Chicago. The probability her first flight leaves on time is 0.15. If the flight is on time, the probability that her luggage will make the connecting flight in Chicago is 0.95. But if the first flight is delayed, the probability that the luggage will make it is only 0.65. Now, what we have here is we've got two different variables. We've got the variable of her flight being on time and the variable of her luggage making it through the connection of Chicago to Denver and making it with her to Denver, okay? Now, as we're looking at these two things, we're thinking, oh, this could be maybe a Venn diagram. And if I think about this as a Venn diagram, I could say, oh, well, this circle would represent her flight being on time, and this circle would be her luggage making it, and this would be the intersection where her flight is on time and her luggage makes it. And in order for this to work really well, what we need is we need them to give us this piece of information, the probability that her flight leaves on time. We really want them to give us this probability, the flight that her luggage makes it. And we also want them to give us this intersection right here, or possibly the sum, the or statement, which would be this plus this minus this, so that we can figure this out. But what they're giving us is this. They're saying, the very first thing, the probability that her first flight leaves on time is 0.15, okay? So that means that this circle here would be 0.15. That's fine. That information is helpful. But then it says this. If the flight is on time, given that the flight is on time, and that's a given statement. That's one of those conditional probabilities. Given that this has happened, the probability of this. That doesn't work well with this. So what we're going to do is we're going to turn around and we're going to try this here. All right, so we're going to start off with this contingency table, and we're going to have two variables. One is the variable of flight, and we've got two choices. Her flight could be on time, or it could be delayed. Okay. The other variable is her luggage, and her luggage could make it to Denver with her, or it could not make it, and we'll just call it make it not. All right, again, it starts off by saying that 15% of the time her flight leaves on time. Now, it doesn't say anything about a condition of making it or not making it or any combination of that. It's just saying that 15% of the time her flight leaves on time, and that value is going to go here, 0.15, 15%. Okay, that makes sense. Now, keeping in mind, as we have a conditional distribution, this value right here is the total of all totals. And if we're talking about percents, this is going to be 1. Because we're talking about decimals here, so this is going to be 1 or 100%. Now, if this value is 15%, meaning that her flight is on time 15% of the time, which is crappy, by the way, that's really crappy, then how often is her flight going to be delayed? Well, that would be the complement of this, or 0.85. So if I have this, I'm given this other piece of information. That's very valuable. Okay, second piece of information. If the flight is on time, given the flight is on time, the probability that her luggage makes it to Chicago is 0.95. Okay, so here's what I'm going to do. I'm going to think about this for a second. Let me wash the board here. Okay, probability of her luggage making it, given that her flight is on time. This value is 0.95. I'm going to put 0.95 here. Okay? If I think about this, the probability of B given A is equal to the probability of A and B over the probability of A. Now, this value right here, the probability of B and A, and I'm going to write this out in the same format. The probability of make it given on time is going to be equal to the probability that the luggage makes it and her flight is on time over the probability of being on time. The probability that her luggage makes it and her flight is on time is this right here, the intersection of these two groups. This is actually what I want. I want to find this value and fill this out. So how can I do that? Well, if I look at this and I think, oh, you know what, this is an equation. If I multiply both sides by the probability of A, which is part of that Bayes rule thing, then I would get this. I would get the probability of A times the probability of B given A is equal to the probability of A and B. Okay, that's fine. I have this value right here, 0.95. I have the probability of on time, which is 0.15. I'm looking for the numerator. So if I take this times this, I'm going to get this value. Now let's go back and take a look at what that means. 95% of the time, when her flight's on time, her luggage is going to make it. Now this is what this is also saying though. And what we just said is I would take 0.95 times 0.15 and I'm going to get this value. But this is what this is saying, and this is kind of like the key here. 95% of this is going to end up here. Now obviously I can't put 0.95 here because 0.95 is not going to add with some other value to get 15%. Because we add down, we add across, that's what happens to get totals. So this can't be 0.95. But what this is saying is going to be 95% of the on-time percentage. So 0.95 times 0.15 is, and I think it's 0.1425. So 14.25% of the time her flight is on time and her luggage makes it to Denver with her. Now, if it happens 0.1425, then this value right here has to be, and I don't want to say the word to complement, but these two values have to add to get 0.15, which makes this 0.0075. Groovy. All right, the other piece of information they're giving me. If the first flight is delayed, given that it is delayed, the probability that the luggage will make it is only 0.65. That does not mean that this is 0.65, because this is delayed and makes it. But they're saying, given that it's delayed, of this population, this happens 65% of the time. So this value right here is 65% of this. So 0.65 times 0.85, as I coughed all over the place, let's find this value here, is 0.5525. All right, and then I add to get this value, or I'm going to subtract in this situation, and that is going to be 0.2975. 0.5525 and 0.2975 add to give me 0.85. And then I will total down. This is going to be 0.6950. Adding down, this is going to be 0.3050. And if I've done this right, these two values are going to add to 1. Groovy. All right, now let's talk about some questions here. A says, are the first flight leaving on time and the luggage making the connecting independent events? Okay, we'll talk about that in a second. B, what's the probability that her luggage arrives in Denver with her? So the question is, what's the probability that her luggage is going to make it? This is if it makes it and it's on time. This is if it makes it and it's delayed. But this is the total of making it. So this is the value right here for making it, 0.6950. That's your answer to B. A says, are they independent? How do I tell if something is independent? And we got to wash the board again. How do I tell if I have things being independent? I would say the probability of B given A is equal to the probability of B happening all by itself. So how am I going to set this up so that I find this? And my suggestion is this, to make life really simple. You're setting up a conditional distribution here. is what you do is you pick the first row and the very first spot. What does that mean as we look at our grid? The very first row and the very first spot is this and the first row. And what we would say is this: the probability that her luggage makes it, given that her flight is on time. So I'm going to write that. Oops, wrong way. The probability that her luggage makes it, given that her flight is on time, has to be equal to the probability of what? Well, it has to be equal to, in this situation, it has to be equal to probability B, or the probability that her luggage makes it. Okay, so the probability that her luggage makes it given it's on time. Given it's on time, we found that value, that's the total of that row, that's 0.15. Because that's our redefining our population, that new population is on time. What's the probability that her luggage makes it? 0.1425. So that is 0.1425. So this is 0.1425 over 0.15. It has to be equal to the probability of her luggage makes it irregardless of what happened. And the probability that her luggage makes it, which just happens to be the answer of B, is 0.6950. So this equals 0.6950. And if these values are equal, then these are independent. But this happens to be 0.95. This is 0.6950. How do I know this is 0.95 off the top of my head? Because I did just the opposite to get this. 0.95 times 0.15 gave me this value, so I'm doing the opposite. I'm dividing instead, and that gives me this, because that's the conditional distribution right there. So are these two values equal? No, they're not. Therefore, are these two variables independent of each other? The answer is no, they're not. All right, so we're going to do 17 in a minute, and not 17, we're going to do 36 in a minute, and then this will become so much easier second time around.